Hi, this is Dr. Bay, and here's Bugsy, and today I'm going to talk about molecular structure. We'll be going over the differences between molecular orbital theory versus valence bond theory, as well as the fundamentals to hybridized atomic orbitals. Stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Today we're going to break down what I think is one of the most difficult topics for a student taking chemistry to understand, and that's orbitals. Before we delve into what exactly those are, let's first talk about where electrons reside. So electrons are confined to regions of space, which are called principal energy levels, or shells. In this diagram, the nucleus is in the center, followed by each shell surrounding the nucleus. The size of the shell increases as it gets farther away from the nucleus, since shell 3 in blue is much larger than shell 1 in red. And as the shell increases, it can house way more electrons within it. Electrons that are farther away from the nucleus exist at higher energies than the electrons that are much closer to the nucleus. Each shell can hold 2n to the squared electrons. So in shell 2, where n equals 2, can hold 8 electrons. And again, the relative energy of the electrons in each shell increases as n increases, as it gets farther away from the nucleus. And shells can be further divided into subshells called atomic orbitals. An atomic orbital is a region of space that can be occupied by electron density with respect to the nucleus within a single atom. Examples of atomic orbitals are the s, p, d, and f orbitals. Recall that shell 2 can hold up to 8 electrons based on the 2n to the second equation. And each atomic orbital can hold 2 electrons. So in shell 2, 2 electrons are in the 2s orbital, and 6 electrons are dispersed amongst the 3 2p orbitals. Atomic orbitals exist as electron clouds and have specific shapes and sizes. S orbitals are spherical, while p orbitals are infinity-shaped and can exist on 3 different axes, the x, y, and z axis. All 3 p orbitals have the same energy and are called degenerate orbitals. Although an electron does not have defined edges, we typically use the term electron density, which is associated with the probability of finding an electron within a particular region of space. And the shape of an orbital refers to the region of space that has about 90 to 95% of the electron density. The other 5 to 10% of the electron density tapers off but never ends. The order in which orbitals are filled by electrons is determined by 3 principles. The Aufbau principle states that orbitals fill in order of increasing energy from lowest to highest energy orbital. And the Pauli exclusion principle states that each orbital can accommodate a maximum of 2 electrons that have opposite spin states. And the Hund's rule states that when orbitals of equal energy are available, but there aren't enough electrons to fill all of them up, one electron is placed in each of the degenerate orbitals first before electrons are paired up. So there are 2 commonly used theories for describing the nature of atomic orbital overlap, and they are the valence bond theory and the molecular orbital theory, or MO theory. The valence bond theory is a bit more simple in terms of its treatment of bonds, so we can start there. So according to the valence bond theory, a bond is the sharing of electron density in which electrons are localized between 2 specific atoms. It's the overlap of atomic orbitals which generates either a sigma or pi bond, which is useful for predicting molecular geometry and shape. All single bonds are called sigma bonds, and a double bond consists of one sigma bond, shown in blue, and one pi bond, shown in green. And a triple bond consists of one sigma and 2 pi bonds. However, oftentimes valence bond theory can be a little too simple when used to describe a much more complex molecule, which is when we can turn to molecular orbital theory. So MO theory describes electrons in a bond that are delocalized between two specific atoms. MO theory uses a mathematical method called the linear combination of atomic orbitals, or LCAO, to combine atomic orbitals to make molecular orbitals. And to clarify, an atomic orbital is a region of space associated with an individual atom, while a molecular orbital is associated with an entire molecule. For instance, a molecule is considered to be a single entity held together by many electron clouds. So MO theory gives rise to bonding orbitals and anti-bonding orbitals. To help explain this, let's take a look at an MO energy diagram for the molecule H2. In an MO energy diagram, atomic orbitals are represented on the right and left-hand sides, with each atomic orbital for H2 having one electron. These atomic orbitals are combined mathematically using LCAO to produce molecular orbitals, a bonding orbital, 1s sigma, and an anti-bonding orbital, 1s sigma star. When each of the electrons from the atomic orbitals combine, they fill the lower energy MO bonding orbital first, based on the Pauli exclusion principle. These two electrons in the bonding orbital are what make the covalent bond, or the sigma bond of the molecule H2. A wave equation is solved to give a series of solutions called wave functions. Each wave function corresponds to the energy of an electron within an atom, giving rise to orbitals. But again, it is the molecular orbitals that describe the behavior of an electron within a molecule. For every molecule, two of its molecular orbitals are of particular interest. One is the highest occupied molecular orbital, or HOMO, and the second is the lowest unoccupied molecular orbital, or LUMO. We'll talk more about how these MOs are involved, especially when various reactions occur, but for now, just be familiar with the terms itself. Let's apply valence bond theory to the bonds in methane, or CH4. Bonding 2s and 2p atomic orbitals would give bond angles of approximately 90 degrees, but instead we observe the HCH bond angles of 109.5 degrees. So why is that? Where is the discrepancy coming from? This problem was solved in 1931 actually by Linus Pauling, who suggested that atomic orbitals should be averaged or hybridized. For example, if we have a 1s atomic orbital and a 3p atomic orbitals, these four can mix together or hybridize into an sp3 hybrid orbital that instead has a tetrahedral geometry with 109-degree angles. And the same can be done when you mix one s orbital with two p orbitals to get an sp2 hybrid orbital that has a trigonal planar geometry with 120-degree angles. And if you mix a 1s orbital with only one p orbital, then you get an sp hybrid orbital that has a linear geometry of 180 degrees. Now let's take a look at the atomic orbital of carbon. Since there are 4 hydrogens attached to carbon, that means carbon has a hybridization of sp3, but we'll get into more detail on how to determine that in a bit. So recall that one s orbital and 3 p orbitals mix together to form the sp3 hybridized orbital. The electronic configuration of carbon is 2s2, 2p2, which means there are 4 total electrons for one carbon atom. If the atom gets excited, one electron from the 2s orbital will move to the empty 2p orbital due to Hund's rule, and then all 4 orbitals hybridize together to form 4 sp3 hybridized orbitals that are all of equal energy, also known as degenerate. Now, using valence bond theory, each of the 4 bonds in methane is represented by the overlap between a sp3 hybridized atomic orbital from the carbon atom and an s orbital from a hydrogen atom. So all bonds in methane are single bonds, and therefore they are all sigma bonds. And the same analysis can be done for ethene or C2H4. First, let's draw the electronic configuration of carbon, and then excite one atom into the empty p orbital. But now only 3 sigma bonds are needed to be made. So only the 2s orbital and the 2p orbitals hybridize to form 3 degenerate sp2 hybridized orbitals. And that leaves us with one unhybridized 2p orbital that is slightly higher in energy. So one carbon atom bonds to 2 hydrogens and another carbon, so we can fill in their respective orbitals accordingly. But that leaves us with a filled 2p unhybridized orbital. So what exactly does that mean? So let's dissect the orbitals and types of bonds that we've discussed so far in the molecule ethene. Ethene contains 4 sigma CH bonds, each made by the overlap of one carbon sp2 hybridized orbital and one hydrogen 2s orbital. So to summarize hybrid orbitals, if a carbon has 4 groups bonded to it, its orbital hybridization is sp3 with bond angles of about 109 degrees. These 4 bonds would all be sigma bonds, and on the right side of the table are some examples of this. And if carbon had 3 groups bonded to it, then it has an sp2 hybridization with bond angles of 120 degrees. 3 bonds would be sigma, and 1 would be a pi bond. And lastly, if carbon has 2 groups bonded to it, it has sp hybridization with the bond angle of 180 degrees, where 2 bonds would be sigma and 2 bonds would be pi.